But today we're going to take a journey to the deepest parts of the oceans, deepest parts on Earth. But before doing that, there's some fundamental points I want to make that may not be obvious to all, and at least it's also once in a while I need to dwell on them as well. And the one thing is we're living on a blue planet. More than 2/3 of the Earth is covered by ocean. It's blue, and we actually occupy only, as you can see, about 29% of it, where we focus a lot of our attention and our work, but the oceans are vast. And the other thing is that the average ocean depth is 3.8 kilometers. There's a huge areas of Earth covered by deep sea. And to sort of illustrate that, I've sort of made this small diagram here where you can sort of see percent of the area of the ocean covered versus the depth interval. So we have about 5% that's covering about 0 to 1 kilometers of depth, and so forth. And you can sort of see that the abyss, which is usually what we define between 2 to 4 to 6 kilometers of depth, is vastly covering the ocean. And then we have a small bit where we're going later today, the hadal trenches, which is from 6 kilometers to the deepest point on Earth, the Mariana Trench at 11 kilometers of depth. So deep sea covers 60% of Earth. And it's to a large extent unexplored, even though that processes in the deep sea are fundamental for the function of our planet. It's fundamental for the chemistry on the planet. It's fundamental for the climate and for how life functions on the planet. So there's a lot of good reasons to explore the deep sea further. The deep sea is characterized by high pressure. We'll get back to that. There's an extreme pressure. We all know the feeling of diving down at the bottom of the swimming pool and sort of feel the pressure on our ears, and that's peanuts compared to what you have in the deep sea. And life there has to adapt and work under these conditions. We'll get back to that later. The other thing that characterizes the deep sea is that it's often mentioned that it's either a feast or famine. There's either a lot of food or there's no food. Sort of illustrated here by an abyssal plain, 6 kilometers of water depth, where you sort of just have mud. It doesn't look like there's much life. There's more to the picture than meets the eyes, but generally it's sort of an example of little life, to a hotspot of life where you have a dead whale that's sunk to the bottom of the oceans and covered by a microbial matters here, or marine snow, which are sinking particles. This is at 2,000 meters depth image, where you sort of see particles sinking through the oceans and providing food for the deep ocean. Another thing we won't have time to discuss so much today is other types of feasts. That is areas where hot, reduced substances are coming out from the interior of Earth and being the foundations of chemosynthetic life that can generate, that can make energy out of these reduced components and build biomass on that. But we'll mainly focus on sort of the upper things here. And then, as I mentioned, the deep sea is largely unexplored. Another point I want to make is that Earth is a microbial world. There's enormous amount of bacteria on Earth. You can sort of see in 10 milliliters of seawater, you will have 10 million prokaryotes of bacteria-like organisms, or 20 billion prokaryotes in just 10 milliliters of sediment. It's estimated, okay, sorry, I have to be here. It's estimated that there's about 5 to the 10 to the 30th prokaryote on Earth. So that's 1 with 30 zeros after. That's a vast number. We can't really relate to that. But to try to illustrate it, if we took all bacteria or bacteria-like organisms, which are in the order of 1 micron, and put them side to side, they would go from Earth and then to the nearest star in the universe, not the sun, the nearest star in the next solar system, which is 270,000 light years away. And they would not do that one time, they would do that 1 million times. That sort of gives a feeling for how many bacteria or bacteria-like organisms we have on Earth. And what they do matters to the chemistry and sort of the life on Earth as such. They're making the foundation for the rest of the life on Earth. And they are very good of feast and famine. They can, if they can get 10,000s, maybe even some people claim millions of years old, if there's very little. With this famine, if there's very little to live on. But if they have a feast, they can double within 20 minutes or maybe even faster. So they can explore conditions like, for instance, in the deep ocean. So let's try to take a look at sort of more of the open or sort of just schematic see the depth of how the deep ocean functions. You can start here at the oceanic ranges where new seabed is formed by magma coming out from the ocean interior, and that is moved slowly through by 5, 10, 20 centimeters per year through the ocean bed, and ultimately this is subducted when the oceanic plate, this new seafloor, is meeting the continental plates and being pushed into the interior of Earth, and that's where we have the hadal trenches. That's where we have the really deep parts of the oceans. During the process of as the seabed is moving through the oceans, it's filled up with sedimentous material. Organic material is produced by photosynthesis in the light ocean, in the surface ocean. Most of that is respired in the surface ocean and turned over in a tight loop here, but some of it is sedimenting down, sustaining life in the deep ocean. And that's why when we move through, this layer of sediment is sort of thickening as we're moving through the oceans as it's accumulating on the seabed. So we have an archive of life during time if we actually just pass through the ocean bed like that. There's also material coming from land, rivers and so on, runoff that sort of sustain life in the deep parts of the ocean. We'll come back to that later. But some of that material is turned over by organisms in the seabed. And now I sort of just wrote microbial here. It's mainly driven by bacteria. It's not entirely fair. Fauna, larger organisms also contribute. On global scale, they contribute about 20%, where bacteria are responsible for about 80% of the turnover of organic carbon in the seabed. And that consumes oxygen, and that releases the CO2 that originally was used or produced when the biomass was formed up here. But there's a fraction that remains here, carbon burial. Some of this material is never turned over. And this is actually what determines the oxygen availability in the oceans and on Earth and the atmosphere. Maybe Don talked about that in his talk as well. So the fundamental regulator of the redox conditions or the oxygen conditions on life is to a large extent, on Earth, is to a large extent regulated by the efficiency by these bacteria to turn over this carbon into CO2, or to what extent it's buried into the sediment record. So that's only one reason for why it's relevant to look at how microbes in the deep sea are behaving. Now, this diagram just shows that organic carbon is taken up by consuming oxygen and releasing CO2. It's a little more complicated than that, but we don't have to discuss that today. I just want to make one point here, is that in the surface of the sediments we have oxygen, and there we have oxygen respiration as we are doing. We are sort of eating organic carbon, using oxygen, producing CO2 and gaining energy and biomass. But deep in the sediments there's a lot of anaerobic processes, microbial life living without oxygen and using other forms of respiration reagents than oxygen as we're using. We'll talk later about a little bit about sulfate reduction and nitrate reduction, but other ways of respiring than using oxygen. But through a complex web of redox processes, these are linked back to the oxygen consumption up here. And that's why oxygen consumption of the seabed expresses the total turnover of carbon, even though that only a fraction of it is actually turned over by oxygen respiration, simply because much of this is reoxidized by availability of oxygen. So how do we measure the oxygen uptake rate of the seabed? And we do that in many ways, and I won't have time to sort of discuss the different rates. Ways of doing that, I'll only refer to one approach here that was pioneered by Niels Peter Revsbæk in Aarhus University. And that's to use microsensors, small electrodes that you can sort of push into the sediment, and then here you have the sediment surface, and then you can record how oxygen disappears in the sediment. Here all the sediment or the oxygen is gone at about 1 centimeter of depth. This is in a summer situation. There's lots of food in the sediment, there's a lot of organic material. This is in the winter situation where there's less organic material, the oxygen penetrates deeper. So in a small cartoon-like fashion here, you can sort of see that oxygen is used partly for the aerobic respiration and partly for the reoxidation of the anaerobic process, the reduced product from the anaerobic respiration. That's why it's worthwhile to go out and measure the oxygen uptake rate of the seabed. You can do that in the laboratory, or you can do that in situ, as Don also mentioned. And of course, one concern is that if you take sediments up from great depth, does microbes, does the thermodynamics, does the physics actually work as it does in the deep sea, or do we need to send the laboratory down to the deep sea to measure the oxygen uptake rate rather than taking the seabed into the lab? And to explore that, as Don mentioned, one of my early tasks was, and others were doing that in parallel, especially in the US, to developing systems that could go down and measure these things in situ. And they are called so-called landers. And we have a number of them here at STU now. I'll come back to that later. But basically, they consist of an electronic package that can do something. You program it to do a number of different measurements. Here, we'll just focus on measuring oxygen profiles in the seabed. You leave it from the ship, it goes independently down, it measures what it's supposed to do and what we program it to do, and then it releases some ballast and returns to the surface with the data. We take it on board the ship, and we sort of see what it has measured down there, and we can, of course, compare that to parallel measurements on board the ship. And one of the early things we found out was the big question was, of course, is this really worthwhile? It's much more expensive, it's much more elaborate, it's much more difficult, of course, to measure things at the seabed than it is to take the seabed into the lab. But what you can see here of data from 30,000 meters of depth in Chile, you can sort of see laboratory measurements here, the open symbols. So they are measured in sediment taken up in the lab. Oxygen penetrates about 2 millimeters. This is measured at 3,000 meters of depth, and it penetrates 6 millimeters. So there's a big difference in what we measure in the lab and in situ. Now, if we plot the ratio between what we measure in the laboratory and in situ, if that ratio is 1, we measure the same. If that ratio is higher, then we measure more in the laboratory than we do in situ. If we plot it with water depth, you can see the oxygen consumption increases with water, or that ratio increases with water depth. That means when we get out to 5 kilometers of water depth, we measure 3 times too much when we measure in the laboratory, and the oxygen penetration is only 20% of what it really is in situ. And that makes it different if we were trying to understand the carbon cycling of the global oceans and the deep oceans and how important they are. If you want quality data, we need to develop instruments that can go down and measure things in situ. There now exist about 800 data points. This is from our last review where we sort of assembled the available data. They're plotted here on the area. And it sounds like a lot of 800, but it only compares to one measurement per the area of size of France. And we all know that if we went down and measured at one point in France, we probably didn't represent France correctly. And that's still the case with the deep sea. The other thing is that there's a bias to where we measure. What we have plotted here is the measurements, the open symbols, and the blue symbols here are actually the actual oceans. So you can sort of see we measure much more at shallow water depth and much more at high production rates than actually the actual oceans. So we overrepresent some areas of the ocean and underrepresent others. But anyway, if we take all the data we have and we plot them, it relates to the water depth, as you can see here. We go down orders of magnitude, this is 2 log-log scales, in oxygen consumption of the seabed as we go deeper and deeper. Now, if we use that red regression line as we have here, and we have the bathymetry of the global ocean, we can calculate how much carbon is turned over in the ocean bed, and it's about 1.5 gigaton carbon per year if we extrapolate those data. That corresponds to about 3% of the global pelagic production, which is sort of a reasonable number. Another story, which I won't discuss so much today, is that it's actually only 7% of the total fossil fuel burning on the planet, telling of how humans currently are perturbating the carbon cycling, that we sort of the entire activity of the ocean bed covering 70% of Earth is only 7% of the fossil fuel burning that's ongoing. But that's a different story. If we look at how that's distributed on the ocean, we can sort of see that even though the rates in the deep sea below 2,000 meters here are relatively low, you can see we go down 2 orders of magnitude. If we integrate it up the area, they are very important. And that's because the deep sea is so vast as it is. But we also see a lot of variations in the data. And why is that? I don't have time to discuss all of these variations, that if we go down at one specific depth, why do we have 2 or 3 orders of variations in the turnover of carbon in the seabed? I'll mention 2 things, and that will take us to the deep hadal trenches. The first thing I want to mention is the surface ocean have different productivity. Here we have derived the algae production, the production that sort of feeds the entire life in the oceans, from remote sensing data, and we can calculate and how much carbon is being fixed and how much oxygen is produced by primary production along different places. All the points here are where we have been measuring, and you can sort of see there's a lot of variation. So that means 1,000 meters of water depth, the amount of carbon coming down depends not only on the depth, but of course also on how the production rates are at the surface ocean. And you can see that from some of our data here we plotted. All of these data are from red areas, where we have one attenuation. This is the oxygen uptake rate. This is the water depth. These are in the blue areas. So we need to account for surface ocean production if we want to explain that variations we saw before. So we can make a simple empirical correlation here that both use the water depth and the primary production. And then we can make maps of how much the ocean bed is consuming of oxygen, how much carbon is being turned over in the ocean bed. The other reason I want to discuss, and that's going through the rest of the lecture today, that is the ocean bed is not flat. One thing is it has seamounts. What you see here is actually at one of our expeditions where we're steaming across the blue ocean here, that's 5 kilometers of depth. Suddenly you see islands like that coming up. That's the peak of mountains that rises up from 5 kilometers of depth, and you just see the peak of the mountain going through the ocean surface. That induces upwelling, that induces deep water, moves up along the mountains and induce hotspots of biological activity. This is where you see the birds, this is where you see the whales, and if you want to have a fish on board, that's where you put out your fishing rods, because here you have the high productivity. But that's the seamounts. Where we want to go today, that's the deep trenches. And you can sort of see these deep trenches here spreading, they're particularly prominent in the Pacific Ocean, as you can sort of see here. The deepest one being the Mariana Trench at 11 kilometers of depth here. How important are they in this equation? And is it so that when we sort of continue going deeper and deeper, that biological activity declines? Or is it actually so that when we go really deep, this is reverted because we have a focusing potentially of organic material illustrated here? So the Mariana Trench, Challenger Deep at about 11 kilometers of depth. Is it so that we have a focusing of food, of organic material here? So actually when we go really deep, biological activity starts increasing again. And to explore that, we developed an instrument that could go down and measure the oxygen uptake rate at the seabed, also at great depth. And what you see here are oxygen profiles measured at the bottom of the trench, the red ones here. You can see oxygen goes away quicker as we move down in the sediment compared to up here at the abyssal plain, where oxygen is consumed much, much slower. So yes, indeed, if we go to the deepest point of the ocean at least, it is so that activity there is much higher than the adjacent shallower environments. Also, when we take our sediment cores up and look at the organic carbon, the pigments of algae, the number of bacteria, and deposition rates of particles, again, we take the ratio here. If the ratio is 1, we would measure the same here and here. If the ratio is higher than 1, we measure more here. There are many more bacteria and prokaryotes or bacteria-like organisms in the trench than there is outside the trench. So these data confirmed, indeed, when we go really deep, biological activity starts increasing again. There's more life and there's more turnover of elements. So to summarize some of facts about the hadal trenches, they're covering from about 6 to 11 kilometers of depth and covering about 3.8 million square kilometers of the ocean bed. There are 27 big trenches, and they act, as we can see, as isolated depocenters for organic material. So carbon is focused from the deep ocean into these trenches, and we'll come back to how important that is as a carbon sequestration measure. They're characterized by an extreme hydrostatic pressure, and they were believed to be deprived of life. People didn't think there was simply life there at all, and that's why they have the name they have, because hadal is derived from Hades, the Greek word for the realm of death in Greek mythology. We now know that they are actually the opposite, hotspots for biological activity and element cycling, mediated largely by unknown life forms, thanks to data as I just showed before. And it's illustrated nicely here, for instance, for the Puerto Rico Trench, where you have the North American plate being subducted below the Caribbean plate. That is pushing up this plate and make these islands here, Puerto Rico and Haiti and the Dominican Republic here. And you can almost, when you sort of look at this extreme bathymetry, wouldn't it be sensible that a lot of the organic material is actually ending up here rather than up here, because you have a focusing of that material. We were not the first to sort of having the idea of trying to explore the hadal environments, and without sort of going in too much detail about the exploration of the hadal trenches, one pioneering team we have to acknowledge is Leonardo Walsh. They were the first one to dive live into the deep trenches. They went into the Mariana Trench in their home-built battyschaft, they called it here. They were sitting into this small sphere here, two guys here, and as buoyancy, they used petrol. So there was fluid petrol. This was full of petrol, and then it was released with a lot of iron plates, and then it simply just sank down to the bottom of the Mariana Trench, sitting down there, releasing the iron plates, and then return due to the lower density of the petrol up here. So that was not a dive where you sort of after successful dive sort of light a cigarette. It's a completely insane achievement. No one was so crazy until James Cameron in 2012, more than 50 years later, tried the same thing. He was fascinating, and he made a lot of money on movies, as you know, Titanic and others. And he was still fascinated by the deep and made his own private submersible and actually went into the Mariana Trench and went a little bit deeper than Picard and Walsh, mainly for exploration and adventure. Soon after, Viktor Veskov, a very rich man from Texas, also developed his private submersible, and he went 13 meters deeper and was very happy about that. So he is now the deepest diving person ever, and he did that in 2019. Since that, he has been visiting a lot of other trench systems, and he's probably the most experienced diver in the deep trenches now. And he's just sold his submersible, but it's actually been a privilege that he's actually led that up to scientists, and we have the opportunity also, some of members of our team and Annie, to join his expedition this summer to one of the deep trenches. So there's partly this extreme adventure and extreme tourism to sort of explore the deep trenches, but there's also very geopolitical incentive to do that right now. And China has a very big program to explore the deep trenches and deep sea in general. That's partly driven by geopolitics and being present in the deep oceans, but also for the hunt of resources. And that's another talk that I won't go into today, but there's a lot of minerals and deep sea mining that has an interest and stimulate deep sea research these days. And China now have the only state-owned vehicle that can actually go down to the hadal trenches. They have not done so yet. They've only been down to 7 kilometers, but they have tested it without people in it to 10,000 meters. This is manned exploration. I would claim that a lot of, if not most, of the scientific advances has actually been gained by unmanned systems like ROVs here, remote operating vehicles that are tethered to the ship, and where you can sit on the ship and move them around and do experiments and film at the seabed. Here are two very nice examples of that, Kaiko and Nexus. Both of them lost now. It tells that it's risky to do deep sea deployments, and there's actually no deep operating ROVs available now. And then there's, in all modesty, instruments like ours here. There are 3 of our lander system here standing on board before deployment at a German research vessel, Sonne here, being ready and being programmed. Kazumasa is sitting here and Morten sitting here, getting the instrument ready before we release them and go down and do the measurements. And that brings me back to the kind of work that we are doing with it. So after the Mariana Trench, we went to a number of other big trenches and saw the same thing. It was not just in the Mariana Trench that actually, when we go really deep, the biological activity and the element cycling rate increases. It was the case other places. But it's very expensive, as you can see, that it's very timely to do these operations. So it took a while before we had funding enough to actually do a more detailed mapping of one trench system. And we went to the Kermadec Trench, which is just north of New Zealand here. And then we measured at a number of sites along the trench and the abyssal plain here. And again, this confirmed what we have seen before, that when we go at the abyssal plain, there's a very deep oxygen penetration, very little biological activity. When we dive into the trench, there's a lot higher activity all along the trench axis. But we also see a lot of variations along the trench axis. And why is that? We'll come back to that. Why do we have these variations along the trench axis, even though the surface ocean production is more or less the same? But generally, from all the explorations or expeditions we've done so far, and where we have time to look at the data, we still have these 2 last expeditions where we haven't really looked at the data yet, but it's about 2 to 6 times higher activity in the deep trenches. If we take all available data from hadal trenches, again, the oxygen uptake rate here, and the surface ocean production derived from satellites, we can sort of see there is a relation. Here, the red dots are from the Atacama Trench, the blue dots are from the Kermadec Trench here, and the single points here are from the single point measurements we did around the oceans, and that's in collaboration with Chinese colleagues as well. And you can sort of see that within one trench we have a lot of variations. So we partly have a lot of variations within one trench. We also have a relation to the surface ocean production, meaning that even at 10, 11 kilometers of depth, we sense what is changing at the surface ocean, and that translates directly to the biological activity at 10, 11 kilometers of depth. You can also see from this slope here, which we don't have to go into now, that there's much more carbon coming down than we can explain by current understanding, at least when we sort of compiled this. So we need, how is carbon coming down to these great depths? And here I would sort of just dwell on two things. One thing is marine snow particles that sort of forms, which we talked about before, these agglutinated particles that forms in the surface ocean and sink down to the deep sea, sustaining life there. They consist of algae aggregates or dead copepods, and looks like a snow because light shines on it, reflects the light, and looks like snow particles. And that's why it has the name of the marine snow. Could it be so that all of the organic material being formed up in the surface ocean, that when it sinks down, pressure increases, and that inhibits the degradation of this material? So is it so that it actually reaches, so when we measure the rate by which this snow particles should be turned over, we do that at 1 bar at the ship, but that's wrong, because it's the microbes sitting in that particle are experiencing a much, much higher pressure. And to explore that, we have developed a number of pressure tank systems here at SDU, where we can sort of measure microbial performance at different pressures, and we can simulate different things, sinking rates and temperatures and so forth, and to sort of see how efficiently does sinking particles degrade. And but we can also look at other, and we do that, I don't have time to discuss that, other microbial performances as a function of pressure. And here's some work of Peter Steve, sitting right here. He's measuring the relative respirations of such a single particle from the surface ocean. And what he has taken one measurement at 1 bar, and then he's taken different pressure ranges. And you can sort of see that when you're up here, there's little effect of pressure because the pressure is not very high. But when you go down, the turnover rate of this, both the bacteria, the respiration of the bacteria, and the turnover rate of the aggregate ceases. So the organic carbon makes it much, much deeper than we intuitively would expect, because pressure is inhibiting the performance of these microbes in the particle. So that's one reason why food make it so deep into the deep ocean. Another thing is that we have a lot of material focusing along the trench axis. I don't have time to go into that, but when you have tide moving in long, deep trenches, it actually physically focuses material along the trench axis, and therefore you have also a physical component that transports most of these undigested material to the deepest parts of the trenches. That also induces a lot of variability we have to remember when we sort of look at these trenches. And this is just measurements with one of these oxygen microsensors along 20 centimeter of sediment here. This is only 3 centimeter depth. This is white line is the surface of the ocean bed, and you can sort of see the distribution of oxygen in here. And if you know something about the distribution and the transport, you can also calculate how fast oxygen is being turned over, and you can sort of see there's hotspots in the sediment where a lot of oxygen is consumed, and right next to it there's nothing being consumed. The reason for that is partly, at least, the settlement of these particles. The food comes down in parcels, so you have a feast where this parcel lands, there's a lot of food, and right next to it where there was no food, there's very little ongoing. And you can sort of see that, I hope it works here, I did before at least, deploying another technique where we actually take images of oxygen distribution and at the same time look at one marine snow particle as it landed on the sediment surface. And you can sort of see how it evolves into an anoxic hotspot there. You can sort of see how small animals in the seabed home in on this, turn it over, and within 170 hours it's gone. Here you have a feast, out here you have famine. So that's the time scale we have to think about too when we sort of think about the life in the deep oceans. Then I want to go to a completely different scale. So we're looking for processes that sort of drive deposition of carbon into great depth. We're looking for variability in the deep trenches. Why is it there? And another reason is seismic activity. So we know these trenches form where you have subduction. There's a lot of earthquakes. And these earthquakes stimulate the deposition of material along the trench axis here. We were fortunate to take advantage of a very unfortunate situation. I think many of us remember the earthquake in 2011 and the big tsunamis that sort of hit east part of Japan. And we were lucky that we could quickly establish, and that was mainly driven by Kazumasa, who's here as opposed to, Kazumasa was involved in that, to take sediment cores, go out only one day of steaming from Japan and sample the sediment and look into the sediments. And here you could sort of see that within very short time, about 30 centimeters, this is a CAT scan where you sort of measure, like you do at the hospitals with the bones, you sort of look at how dense they are, and you can look how dense the seabed is, and you can sort of see that here there's a deposition of about 35 centimeters of sediment that happened very quickly. That's confirmed by this measurements of lead-210. We'll come back to that in a little while. Lead-210 is a particle that measures how quickly things settles at the seabed. When that's vertical, it means it settles very fast. If it's declining, it settles over longer time scales, and we can calculate how fast it is. Just close by, there's only about 5 centimeters of material settling there. But one thing that surprised us really was that we found cesium-134, and that could only come from one place, the Fukushima nuclear power plant. So that means 4 months after the tsunami and the meltdown of the reactor here, we could see the signal of that reactor or the radionuclide waste in one of the most remote places you would anticipate, one of the most remote places in the Japan Trench at 9.5 kilometers of depth of the trench. And that tells us something about the connectivity, that how fast you can actually move material from the coastal ocean and maybe even from land into the deep trenches. I'll just use again here sort of one example of that where you sort of see the lead-210 and look at the dynamic that is happening during such depositions. So here, this is from Atacama Trench of Chile, and you have the lead-210 here. So the lead-210 being a proxy for the rate of deposition of particles. You can sort of see you have a steady decline here, which tells us we have a steady depositions of material, which is about 0.4 millimeters per year of material settling there. But then in 1929, we had an earthquake that we just saw before, and you had 8 centimeters of material being deposited here. So within a few days, you have deposition that corresponds to several hundreds of years of deposition. And you can sort of see that it's enriched in organic carbon here. You have higher carbon down in these environments. That's happening here. And you can see those traces when you take up a sediment core from great depth. You can sort of see the laminations of these different deposition events. Some cases it's volcanic ash that's deposited, other cases it's organic material that's deposited. And from that we can calculate how much carbon is actually make it down to these trenches. And during the big earthquake we looked before, it's 1 teragram of organic carbon that was translocated to the interior of Japan Trench. It's difficult to relate to these numbers, but it's actually a significant proportion of the global production of carbon in the oceans that's within a few days is translocated into the interior of the Japan Trench. And much of it is deposited below the oxygen penetration depth. We'll come back to that in a little while, why that is important. If we look at the mass accumulation, that means how much does the seabed grow versus water depth, we sort of see less and less being deposited as time goes, as water depth increases, and you can sort of see that less and less is getting down. But if we include now our new data from the trench systems, we can see when we go really deep, actually you get up to deposition rates of material that scales to what we have in many coastal oceans. And if we look at how much of that organic carbon that's sequestered in the sediment, that's being left, being buried in the sediment, in the deep trenches, it actually scales to highly active coastal environments. And if we take the carbon burial rate in trenches as such, it's 70 times higher than it is on the deep ocean average. So that means even though they only cover 1 to 2% of the ocean bed, there's a significant proportion of carbon that's sequestered. That's a very important climate feedback because we're storing carbon in these deep trenches, organic carbon that's fixed at the surface ocean or translocated into the interior of the trenches that is stored there. So that's one reason for why these trenches are very important. Now, much of this material is then deposited in oxygen-free environments, as we saw before. Here we have oxygen penetration depth that's shallow at Atacama Trench or at Kermadec Trench, just as two examples here, and much deeper oxygen penetration we would go into the abyssal plane. So what is happening when we go down below the oxic zone? There we have the anaerobic world and other processes are taking over, and one process that would be relevant to look at is anamox. That's a process where ammonia is oxidized by nitrate that gives energy, and a special group of bacteria can harvest that energy and use it for growth. And we measured the distribution of anamox activity in these sediments, and here you have the activity in two different trend systems. We took the DNA and sequenced the DNA, and so there was a perfect alignment between the distribution of these special bacteria and these activities in the sediments. So why does that matter? Well, that matters because we are removing nutrients that can be used for growth of algae and other organisms in the oceans into inert dinitrogen. And in these two trend systems, you can see the rates here in these units here, and the percentage about 70 to 90, almost 100% of that turnover rate was reduced due to these unique bacteria. So condensed in this diagram here, what you see is that in normal deep sea, as we thought before, organic carbon was mineralized, producing ammonia, and nitrate was liberated to continue growth and being in the deep sea. But in the hadal trenches, it's actually removed. Almost 80% of the nitrogen is removed in the hadal trenches. So that's another important factor for the hadal trenches and why they are relevant to study for understanding the global cycling. I'll skip this for now. So who are these anamox bacteria? Because that's one question, where do they come from? And without going into too much detail, we've been sequencing the DNA, of course, of these type of bacteria and sort of see where do they come from. And the great surprise for us was that they were highly diverse, coming from very different environments. We had actually expected there were specialists that were capable of doing these activities at these special conditions in the hadal trenches. But it appears that we actually have a lot of diversity and variability in microbes that can operate at these trench systems. This is for the anamox bacteria. We're still looking for other types of bacteria if that's true for all over. Because another process that is important, as we mentioned at the very beginning of the talk too, is sulfate reduction rate. That's responsible for more than 50% of carbon turnover in Odense Fjord, for instance, where you have bacteria respirating with sulfate. And indeed, we also for sulfate reduction at these deep trench sites. The product of these sulfate reduction rate, the reduced iron, reduced sulfur and reduced iron, we also found in the sediments. So indeed, in contrast to what you would ever expect is that in these deep sea environments, you actually have a full redox cascade and anaerobic turnover of organic material. And that's responsible for a significant part of the turnover of carbon in these systems. Some of the open questions are, of course, where does these anaerobic organisms come from? How unique are they? How do they adapt? How do they evolve? And how are the linkage? What is the diversity? If we go into the different trench systems, are they different? Are they unique? Or is it like Darwin's finches, that they have different finches on each island? Is it different anaerobic communities you have in different trench systems? Now, I talked a lot about bacteria, and that's because that fascinates us and the biogeochemistry. But we also collaborate, of course, with other people that are looking at more higher fauna. And some of those data I would like to show here. This is work from Alan Jamieson's group, where they put down a camera, they put some bait here, a dead mackerel, send it down, and then they come and see who eats it. And they put a baited trap here, where they put food inside the trap. Here is what's happening at 4,000 meters of water depth. Here the mackerels are falling down through the water column, settling at the seabed, as you can see here. And in this case, you get deep sea fishes coming, feeding on it. When you did that, when these experiments were done the first time, no one knew these fish. And if you calculate how fast they home in on this and the abundance of them, it actually turned out to be one of the most abundant fish in the world. So tell us how little we know about the deep oceans. The ballast is released, the instrument is returned to the surface with whatever it captured in its trap. Well, let's first try to go deeper. So now we're going to almost 7 kilometers of depth here. See the mackerel sinking down again. Now it's too deep for fish. There are no fish down there. The physiology does not allow them to work at such great depth. But they are amphipods, living on carcasses or of each other, and peeling off this skeleton quickly. So if you look into what's caught in the trap, a vast variety of different amphipods, many of them unknown at that point when these kind of experiments were initiated. And what you also found was there was a big variations in the size of these. In cases that you had a big one in there, that was the only one you found because it ate whatever came into the trap. So they are fiercely carnivores. And what Alan thought about doing, well, what was one of the big ones here, was to, okay, is it only organic carbon that's focused at these great depths? Is it only organic carbon that stimulates biological activities in these sites? Or is it other things as well? And he looked into the level of pollutants in these amphipods at the very remote places in the deep ocean. And he actually found rates of persistent organic pollutants there that scales to what you find in very polluted areas in China. So it's not just the organic carbon, it's also pollutants and other elements that ends up in the deep ocean. And we found very, very high, up to 60 times higher enrichment of mercury in the deep trenches compared to the abyssal or the deep sea in general, showing that it's also the trace elements are also accumulating in these areas. And just as a last thing here, just to sort of show how unknown and how little explored the deep ocean is, during just one deployment during our expedition to the Atacama Trench, Alan took images of 3 unknown species of fish just in one deployment. Unfortunately, we only caught one of them in the trap, so that's the only one that can sort of really be ratified and described and be acknowledged as a new species, but it tells us how little we know about the deep ocean and how much there's still to explore there. So, take-home message from the talk here today is that trenches are different. They function entirely different, and we cannot understand how they function by extrapolating what we know from shallower environments. They are depocenters with very high sediment accumulation, very important for carbon sequestration on the global scale probably, and very high levels of inventories of pollutants. But at the same time, they're very dynamic hotspots with a very high diversity and intense biological activity. And they have a very high degree of spatial variability, both within trenches and between trench systems, and very dynamic depending on the deposition dynamics from the surface ocean, seismic activity, earthquakes, and tidal dynamics. And they host the full range of processes we actually know from coastal environments, which was really a new discovery. They act as sinks for nitrogen in the global nitrogen cycle. But there are still many open questions. We still don't fully understand the biogeochemical significance of these trench systems. Who are the microbial and myofaunal key players? And there's a lot of new research areas opening. One thing we just touched on here, the hadal pollutants. Deep sea explorations, there's a lot of rare earth minerals available in the deep sea. And what are the challenges of exploiting that, and what are the limitations, or should we do it, and so forth. And another thing that's a little nerdy here is just we started a small collaboration with the bioacoustic group in biology. What is the soundscape down there? Are there sounds down there? Is sound a communication form? And how does it sound at 10 kilometers of water depth? With that, I would like to thank a lot of collaborators and students and technicians that really have contributed and driven much of this work, and the funding agencies, most importantly, the Danish National Research Foundation, but also the ERC and FNU, and the Japanese Research Council, helping us support the Danish Center for Hadal Research. Thank you.
Any questions? We have about 10 minutes for questions. Det til optagelsen den mikrofon.
Okay. Well, thank you, Ronnie, for a very interesting talk. I come from geopolitics, so this was mostly new to me. I was struck by one thing you said, which was that China is very present because to be present and to look for resources. Could you inform me a bit more? What are the resources they hope to capture and exploit? Because this is, after all, a very hostile environment.
Yeah.
Thank you.
First of all, I mean, China want to be present also and be a political player in the deep oceans. There's a territorial, especially in the South China Sea and also towards the Pacific Oceans. But there's a lot of rare earth minerals, elements that accumulates, that we use in our mobile phones, or we use in car batteries, that are accumulated and can be mined in the deep oceans. They form small nodules that are displayed at the seabed, and you can harvest them. It's quite expensive now, but it's actually becoming favorable to exploit them now because prices have gone so much up on rare earth elements. So clearly you want to be present and get allowances to harvest the rare earth elements in those areas, and very often that means presence. You have to be present there and make a claim for these things. So there's a race right now among big players, both nationally but also big companies, to sort of be present in the deep ocean and be a part of that adventure of exploiting these elements.
Super interesting talk, Ronnie. And it's so fascinating how life evolved to live at 10 kilometers of depth in the ocean. And I'm interested to hear the bacteria you find there. How are they evolutionarily connected with bacteria at the surface? So has there been a connection over time of evolution between the surface and the depth? Or did they settle there and had their own evolutionary development? Yeah.
That's a great question, and we are also asking ourselves that. Obviously, because you have a constant inflow of DNA you have a constant inflow of organisms to this great depth. And we don't know, first of all, how easy is it to adapt to high pressure? That's one thing to look at. Is it something they can do quickly? But the high diversity and the apparent high activity of many microbes that actually make it down there contrast to what we sort of see with our particles, where we sort of see reduced activity in the particles. But maybe it's so that we have microbes that are sitting down there and actually sub-performing, but performing enough to sustain life. They're not optimized for it. And over time, you evolve organisms that are better adapted to these conditions. That's a particular challenging scenario if you think about anaerobic organisms, because they have to be moved around without oxygen. How do they make it down there? Or can spores-forming anaerobes make it down there and actually, over time, adapt to being more fit for the conditions that you have at these extreme pressures and low temperatures, and very infrequent supply of food? We don't know, and that's one of the really fascinating things that we're looking at.
DNA sequencing doesn't reveal any of those interlinks.
Not as far as we are now. We don't know how deep we have to sequence to really see an imprint of piezophilic behavior. So if pressure affecting it, what we can see is there's a surprisingly high diversity. And we can sort of see much of that diversity is also represented in other environments. That should not eliminate the potential that you actually have microbes that are specially adapted to this high pressure, and they are actually doing most of the work in some context. But we miss them in the way that we have been looking at it so far. But that's where we're heading in.
Yeah, thank you, Ronnie, also for a very interesting talk. I'm thinking a little bit about maybe a non-scientific question for you. As I know, you spent a lot of time planning these cruises, months and months in the lab. And then I know when you are out at sea, the sea can be calm, but it can also be rough. And you are working on 10 kilometers depth. I'm just wondering, how successful are you with the sampling, and yeah, how much do you get with you back compared to what you actually planned?
If you had asked me 4 months ago, I would have said, great. I mean, we are very successful. But we have just had 2 expeditions that were challenging. The one in the Southern Ocean, I mean, just waves of 10 to 12 meters. I mean, it tells itself that it's not easy to work with these conditions. Generally, we have been very successful, and we had, before these last 2 expeditions, we have never lost an instrument and always recovered samples. That didn't happen this time. So it is a risky chance to take. I mean, of course, we also do a lot of work back home. We have all the pressure tanks systems to sort of understand how pressure affect performances. But of course, one of the backbones of our work is to get out and get fresh samples and to do work on ship on fresh samples and to use our remote operating instruments. And that is challenging, but we feel, relatively speaking, we're good at it. But we have lost 2 instruments here recently. And yeah, not to talk too much about it, but just at the last cruise, we also lost an instrument. Oh, it's still standing out there, but we had to leave because there was a medical emergency on the ship that we had to go to a hospital, and then we had to leave the instruments, of course, and then we can't get back. And so there's all of these things that goes into when you're sort of operating these big expeditions. There's an element of chance.
Thank you, Ronnie, for an inspiring talk. Also being from the social sciences, like Sten, as you know. I wonder if now we have experienced a number of centuries of linear extraction economies and their disturbing effects on geobiological systems, which is one of the reasons why we have Sebastian's Center in this building on climate change. Do you have any idea about some of the systemic risks that would follow from an exploitation of the hadal abyss resources of rare earths? In other words, which kind of systemic relationships might be in jeopardy from such an exploitations?
I don't know so much about it from a social point perspective, social science, but biological.
Geobiological systems.
Of course, you cannot exploit these systems. They are very slow growing without destroying them. They are very slow growing. The growth of a manganese nodule with the size of my fist had taken millions of years. It's rich, but it doesn't regenerate. You can cut down a forest, the forest will be there in 30 years. When you exploit these things, they do not regenerate. That's not an argument for not using them, but you have to be very sensible on the way that you do exploit them, because it's a finite resource. The other thing is that the way you do it is that when you can sort of see the sediments here. I mean, if you want to harvest all of that material there, you generate enormous plumes of sediment that has a lot of consequences for life down there, but also consequences for moving material around with ocean currents and so on. So there are many thoughts that has to go into how do you want to exploit that, to what extent should we do it, and that, well, that's an ongoing debate. But of course, on other fronts, there's a competition for this, and there's a lot of financial pressure for starting this development. Yeah.
Yes, also one question from me. Ronnie, now we're seeing like a changing climate system. We see more energy in the oceans. We see like a lower pH value. So what would the consequences be if you go back like in 10, 15 years from now?
Acidification-wise, I'm not concerned about the deep sea on a timescale of 10 to 20 years. What is changing and transforming is the surface ocean productions and also ocean currents, which may displace production areas. Upwelling would intensify most likely, especially in the Arctic regions where you sort of have ice going away, you enhance the upwelling systems, generating higher productivity. And as we saw on these maps, I mean, that translates all the way down to the seabed at 10 kilometers of depth, in Central Arctic, 5 kilometers of depth. You would sense that in the way that more food will be channeled down to the deep sea. The consequences of that might be, of course, a changing of these systems. It might also be higher carbon burial, which is a good feedback for the climate system as such, but it will certainly transform many of these biological systems that we have down there, favorizing organisms that are good in adapting to higher input of organics versus the ones that have adapted to very low inputs of organics. But it will be very different places. You have the big ocean gyres where productivity probably will not change so much, but there's other areas where you would have very high change in productivity.
I think that's it. Thank you so much, Ronnie.
Yeah, thank you.